Okay, so hi everybody. It's a pleasure to have Michael Bronstein for this first keynote of the day. So Michael is a DeepMind professor of AI at Oxford, on the previously held appointments at Imperial College London, TU Munich, Harvard, MIT, and Stanford. And he was the head of the graph learning research at Twitter, which now is X. It's a pleasure to have him. I give you the floor.
Thank you very much. So great to be here. I hope you can hear me and see me. And yeah, so today I would like to talk about deep learning on graphs. Well, graph neural networks, as probably some of you are familiar, and how we can we approach these problems from the perspective of physics. And maybe allow me to start from a little bit far away. I usually like to open with this quote from Weil, who said famously that there is one concept that is very important, which is symmetry. And it's one idea by which humankind through the ages has tried to comprehend and create order, beauty, and perfection. So the term itself is actually from Greek, and ancient Greeks believed that symmetry plays a fundamental role in the universe. So Plato, for example, thought that what we nowadays call Platonic solids, these symmetric polyhedra, these tiny little polyhedra, are probably the basic building blocks of the universe. So they're so perfect, so important that probably they make up all the matter around us, which is not such a wild idea if you think of it. That's how crystals are organized, right? And Greeks are also famously credited with, if not inventing, at least formalizing geometry, that we still probably teach as the geometry at school, Euclidean geometry, and the famous 5 postulates of Euclidean geometry described more than 2,000 years ago. And as you probably know, there are 4 of them, and the 5th one somehow stood out. They were the one about parallel lines. And many illustrious mathematicians try to prove it or disprove it, and to no avail, until the beginning of the 19th century, where suddenly came the realization with the first works of Gauss, Lobachevsky, Boyer, Riemann, and others, that you can actually define a world of geometries that are not restricted by the 5th postulate of Euclidean geometry, what was given the name of non-Euclidean geometries. And they created this kind of zoo of different things that were not clear how they're related to each other, what actually defines a geometry. So it was a somewhat unhealthy situation until came in Felix Klein in 1872. And he was very young, only 23 years old, when he got an appointment as a professor at the University of Erlangen. And he was asked, as this was customary, and probably still customary in Germany, to deliver an inaugural talk about his view on geometry and mathematics in general. And this entered the history of mathematics as the Erlangen program, where he proposed an algebraic approach to geometry, defined geometry as a space plus some group of transformations. So essentially, you can look at objects that are transformed in certain ways by applying some group, and then see what kind of properties are preserved or remain invariant. And for example, classical Euclidean geometry is obtained from applying rigid motions. So if you take an object and you move it around, right, by translating it or rotating it, or you can also introduce reflections that change the orientation of the coordinate system. And then basically you get Euclidean geometry. And you can extend it to bigger groups, like a fine group or projective group. And he was also one who was able to formulate what is in this nowadays described by differential geometry, hyperbolic geometry with negative curvature through projective transformations. So this was a very important result in geometry. So it took about 50 years to incorporate in full Riemannian geometry, mainly by the works of Élie Cartan in the beginning of the 20th century. And it also had a big cultural impact in mathematics. So continuations, maybe in a more abstract way, of the Erlangen program gave rise to category theory, for example, which is the language of abstract mathematics nowadays. But arguably the most important impact was in physics, where also about 100 years ago came the realization that actually the laws of the universe can be derived from first principles, conservation laws, like what Noether's theorem states, that you can derive certain conservation laws in physics from symmetries of the underlying system. And in some incarnation, this became known as the standard model. So this is more or less all the physics that we currently understand. There are some probably other things that we don't, but at least this is how it looks like. So you can argue that you can derive modern physics entirely from considerations of symmetry. I think physicists like to distinguish between the external symmetry of the space-time, right? The Poincare group that gives rise to the Minkowski geometry of the relativity, and the internal symmetries of the quantum fields that give rise to different forces and different interactions. So long story short, I think it's best summarized by Philip Anderson that it's only slightly overstating to say that physics is the study of symmetry. Now, you can ask, what does it all have to do with deep learning and machine learning? So in deep learning, we also have this similar situation to what happened in the 19th century with different types of geometries. We have different types of neural networks that historically were derived for different types of data and different considerations, different problems in mind, like convolutional neural networks came from applications in computer vision, in image analysis, or recurrent neural networks were derived for time series, for sequences. And apparently these are completely disconnected pieces, and people, when talking about deep learning, they say, well, this is some kind of collection of hacks. You don't really need to know mathematics in order to do research in this field, which in my opinion is not true. And with what we call geometric deep learning, we try in the spirit of Klein-Erlangen program to bring some common denominator, some solid mathematical foundation to deep learning. Basically what we show is that you can derive existing architectures, most of the popular deep learning architectures, from first principles, symmetry, and some other considerations, as well as actually get a general blueprint that allows you to invent new architectures for problems that might appear in the future. So if you look at a simple setting of machine learning, right? So the classical example of cats and dogs, right? You have inputs, images of cats and dogs, and you want to tell them apart. So some people maybe a bit cynically say that machine learning is just glorified curve fitting. So you have a high-dimensional space, right? You have a function that gives you a binary label, cat or dog, right? That basically you try to fit this function from samples that you observe. So you know examples of a few cats and a few dogs, and you try to interpolate and extrapolate this function. And what the question is what to put in this black box, right? So what will be the right mathematical abstraction or a class of functions that you would like to put here? And we know already for decades that a good candidate are neural networks. First examples of these neural networks, perceptrons, were invented in the 50s by Frank Rosenblatt. And we know about them that even a very simple system of two-layer perceptron has the property that is called universal approximation. So I can give you any continuous function, and there exists a two-layer perceptron with certain number of neurons and certain parameters that would be able to approximate this function to any desired accuracy, right? So it doesn't answer the question of how many neurons, right, and how to find these parameters, which makes machine learning sometimes a difficult problem, but at least in principle it exists. Now, of course, if you come from mathematical perspective, then you would say, wait a second, we have infinitely many ways of passing a function through a set of finite points. So we need to impose some assumptions about this function, right? So this is what typically mathematicians call regularity. So it's a function that is not arbitrary, it behaves somehow well, right? And there are standard notions of regularity that exist in approximation theory. So you can start, for example, with what is called Lipschitz continuous functions, right? Functions that, for example, have bounded derivatives. And the problem is that these results do not work well in high dimensions. So if you take a very well-behaved function in 2 dimensions, then you can say that I can have a small number of samples that I can sample it. But if I start growing the dimensions to 3 to 4 and so on, this bound will scale exponentially. So it will look like 1 over epsilon to the power of d, right? And even if epsilon is very small and d is something modest, right, maybe 1,000, right? So that's very modest by modern standards in machine learning, then the number of samples you might need to take will be bigger than the number of particles in the universe. So it's definitely not tractable. Now, you can also see that if you look at images, right? So images are a good example of very high dimensional inputs, right? So even a very tiny image of 30 by 30 pixels is almost 1,000 dimensional. And if I treat it as a vector, as a d-dimensional point in d-dimensional space, then you can see that somehow we completely throw away the geometric structure of the image. So if I take this digit 3 and I want to classify it, I parse it into a vector and feed it into the simple perceptron neural network. You see that just a shifted version of the image just by 1 pixel will look completely differently. So what in this case we'll need to do, we need to do what in modern day terminology is called data augmentation. So I need to show the neural network a lot of shifted versions of the same digit in order to teach it that it should be classified with the same label. And this realization gave rise to a new class of architectures that emerged in the 80s, first inspired by results in neuroscience on the organization and the function of the visual cortex. And it was famously first the neocognitron of Fukushima, and then the classical convolutional neural network architecture of Jan LeCun. So the key concept here, maybe without explicitly realizing it, was to take advantage of the structure, the geometric structure of the data, in particular in the form of local shared weights that can be implemented as a convolution operation. And maybe looking at it from different perspective, we don't need to consider our input as just the dimensional vector. We need to consider it as something that lives on a low-dimensional geometric domain. In this case, a plane or a grid. So here's an example of how an image looks like, right? So it's a function or a signal that lives on a grid. And now the grid can be described by some symmetry group, right? So we might have some class of transformations that are interesting in our problem. For example, in object recognition, I don't care how the object is translated in an image or on a grid. I want to still be able to say that, like in our example of this digit classification, that it's still the same digit, right? So if I describe it using a symmetry group, a group of translations in this case, then this group acts on the data that lives on the domain, so what is called group representation. In this case, it will be the shift operator. And now I can implement functions that respect this symmetry in some way. And this gives a very general blueprint. So you choose your geometric domain, you choose your symmetry group, you define signals that live on this domain, and you have appropriate representation of this group that acts on these signals. And then we have functions that are either invariant or equivariant with respect to symmetry, right? And we'll define it in a second. And the classical example of convolutional neural networks is exactly this, right? So you have a grid, you have a translation group, you have images that live on this grid. The translation group acts on them through the shift operator, and then convolution is a linear equivariant operation, right? You can actually define axiomatically convolution in this way. So it's the only linear operator that commutes with shift. Another example that I will be talking more in detail about today is graph neural networks. So in this case, the domain is a graph, and the natural symmetry of the graph is the permutation of the nodes, because we usually don't have the canonical ordering of them. And the functions, as we'll see, will be implemented in the form of message passing, will be equivariant with respect to these transformations. Now, these are the symmetries of the domain, right? So this is the kind of external symmetry in physics, right? The symmetry of the space-time. What about the symmetry of the data itself, right? So the analogy of internal symmetries. So if we have, for example, a graph that lives in some space, what is called geometric graphs, think of a molecule, let's say, then you can also associate some symmetries with the coordinates of the nodes. And this is, again, very typical in chemical applications where you can take a molecule and you don't care how it is positioned in space, right? So I can rotate or translate it, but the physical properties of the molecule will not change, right? So I want also some form of symmetry with respect to these transformations, and this is called equivariant graph neural networks. They've been famously used, for example, in DeepMind's AlphaFold 2 for protein structure prediction. And basically, this is a very general principle. You can apply it to many different geometric objects, and as a result, you will get many different popular architectures, whether it's classical CNNs or maybe deep nets and point nets or graph neural networks or the famous transformers or some versions of recurrent neural networks and so on and so forth. So you can derive all existing and probably many future architectures from these basic principles. Now, let me say more about graphs. And graphs, as you probably know, they are a very common mathematical abstraction for practically anything, right? So any system of relations and interactions can be mathematically modeled as a graph, from very small scales like molecules to very large scales like social networks. So in the simpler version, you can think of a graph as a collection of unordered pairs of nodes, right? So nodes, models, and objects, some entities. They have some associated features. I denote them by X, right? And the edges are undirected. So we have an unordered pair of nodes. And if I want to represent this object on the computer, right? So it's purely topological construction, right? So we have a notion of how things are connected, but we don't have anything beyond this. We can represent it as matrices, right? So I can represent the features as a matrix of size n by d, and the structure of the graph by the adjacency matrix of size n by n, right? So n here is the number of nodes, and d is the dimensionality of the features. Now, the key problem here is that we don't have a canonical way of ordering the nodes. So by representing this graph as these two matrices, I impose some ordering of the nodes. But if I impose a different ordering of the nodes, then I need to permute the rows and the columns of these matrices, right? And there are n factorial many ways of doing this. So any problem of dealing with graph structure data comes with this built-in ambiguity that we need to address. And the kind of problems that we typically are interested in are of the graph level, right? I give you a graph and I want to predict the property of the entire graph, like in problems in chemistry that I mentioned. I give you a molecule represented as a graph and I want to predict, for example, its solubility or whether it's toxic or how it binds to a target protein, right? That is used for drug discovery. Or in example of social networks, I give you a graph and I want to predict node level properties. I would like to say, for example, that the user is a spammer. So in the first case, I'm interested in functions that no matter how I change the order of the nodes, the result will be the same. So these are permutation invariant functions, right, that respond in the same way to permuted input. In the second example of problems, the structure of the output is the same as the input, right? So we have node-wise output. So if I change the order of the input nodes, I want the order of the output nodes to change in exactly the same way. And these functions are called permutation equivariant. Now, graph neural networks, and in general, you can argue that most deep learning architectures are a collection of equivariant functions, right, implemented as layers of a neural network that create some node level representations that then are pulled together into a graph level representation. You can say the same thing about convolutional neural networks, for example. Now, the way that these equivariant layers are implemented are through some neighborhood aggregation. So we take a node in the graph and we look at its neighbors, right? So we have a soup of features that the node sees. And this soup appears in an ordered way, right? Because I remind you, we don't have a way of ordering the nodes in the graph, typically. So when we aggregate this information, we need to do it in a way that is agnostic to the order of these features. So it must be a local permutation invariant function, right? Like sum or maximum or average. When I do this operation now at every node of the graph, I get a result for every node of the graph. And you can easily see that if I permute the inputs, then the outputs will be permuted in the same way. So it's permutation equivariant function. And there are many ways in the literature that you can implement it. So we call these the flavors of GNNs. And you can just look at, for example, averaging of your neighbors, maybe transformed in some parametric way that is learnable. So these are convolutional architectures, right? The way that the aggregation works depends on the structure of the graph. You can make it slightly more complicated. So you have still averaging, but with coefficients that depend also on the features. And this is how attention works. And then you can have the most general message passing, where it's just a function of two inputs. And it depends both on the features of the node and of the neighbors. And there is a resulting graph theory that is called the Weisfeiler-Lehman graph isomorphism test. And it was shown under some technical conditions that if you choose appropriately this aggregation operation in message passing, then message passing neural networks are as expressive as the Weisfeiler-Lehman test. So if you ask what kind of functions can you represent by a message passing graph neural network, right? Unlike, for example, with the very general expressive ones that can represent anything, any continuous function, here you're restricted to anything that can be distinguished by the Weisfeiler-Lehman test. And what is this test? So it's an iterative color refinement procedure. So it starts with a graph that is featureless, and it tries to characterize the neighborhoods of every node. And initially in this graph, we have nodes or neighborhoods of two types, right? We have node with two neighbors and node with three neighbors. And if I choose wisely this local aggregation function, if I make it injective, right? Think of it as some form of hashing, then it will produce two distinct labels, right? Or distinct colors. So now I have refined coloring of the graph, and I can repeat this procedure again. Now I have three types of neighborhoods, right? As shown here. And at some point, this color refinement procedure will stop, at which point I will produce the histogram of colors. And this will be kind of graph level description. And the algorithm tells that if I give you a graph with different histogram of colors, then the graphs are not isomorphic, so they're structurally different. I can not permute one adjacency of one graph into another. But if the colors are the same, like in this example, we actually don't know. So it's a necessary but insufficient condition for isomorphism. And in fact, we can find counterexamples of non-isomorphic graphs that would not be distinguishable by the Weisfeiler-Lehman test. So it is failed by very simple examples like what is shown here. So from the theoretical perspective, Weisfeiler-Lehman gives us a nice formal framework to analyze the expressive power of graph neural networks, right? What kind of graph functions can be computed by a graph neural network? On the practical side, well, we run into this problem of ambiguities, right? So some non-isomorphic graphs will be tested by WO, and also from practical perspective, some graphs might be unfriendly for message passing. So if I need to send information from one blob to another and they're connected by this bridge, then I need to squeeze all the information through this bridge, and information might be lost in the way, right? So we might have problems of bottlenecks and what is called oversquashing in the literature. So to the first problem, there are solutions, for example, in the form of extending the tests to higher order tests, considering not only nodes, but tuples of nodes. And again, there are some classes of graphs that cannot be distinguished, but they're diminishingly small. And there are equivalent implementations of graph neural networks that are formally equivalent to these tests. Now, for the second problem, what is commonly done is what is called graph rewiring. So I can decouple the computational graph from the input graph and try to make the graph more friendly for message passing. For example, if I have this narrow bridge, I can maybe add a few links so the information flows better. The problem, of course, that it breaks this nice link between theory and practice. So now I use a different graph, so I cannot analyze it using the Weisfeiler-Lehman formalism. So if we look again, take a step back and look at how graph neural networks evolved in the past decades, then the initial assumption of a graph neural network was that you are given an input graph and you use it as a computational device. Send information on the same graph, and then by doing this, you also discover maybe to some extent its structure. But of course, you can incorporate some extra information. You can incorporate what is called positional encoding or structural encoding. This is what transformers use, for example, popularly. You can lift the graph into a high-dimensional topological space. So instead of considering nodes and edges, right, zero-dimensional, one-dimensional spaces, you can also consider, for example, cells, right? So higher order structures. You can consider collections of subgraphs that are extracted by using some policy. And there is a nice link to what is called reconstruction conjectures in graph theory. Yeah, as I mentioned, you can consider also the symmetries of the data, and maybe in some special cases, when the graph has a particular structure like a grid, then you can make message passing more specific, and then you maybe recover back the convolutional networks. So basically, the common topic of these different architectures is introducing more structure, sometimes inventing more structure to make message passing more interesting. On the other side, you can also ask the question, can I use a different graph, right? So in the extreme case, you can completely discard the graph and say, I don't trust the graph, I just use the features of the nodes. In this case, you get a set, right, which also inherits the permutation ambiguity of the original graph. And these architectures are very popular, for example, for analyzing three-dimensional point clouds in computer graphics, deep sets or point nets. On the other extreme, you can allow any pair of points to interact. So you say that my graph is fully connected. I would like to learn the right graph for the task based, for example, on the attention mechanism. So I will learn some kind of softly weighted edges of the graph. And this is how transformers work. Right? Transformers allow you to interact potentially any pair of nodes in the graph, right? And you probably know that they are now the common architecture for natural language processing applications. So somewhere in the middle, say these methods that I called graph rewiring that blend the two options. So I can be maybe close to the graph that is given to is the input, but not necessarily stick to it as such. Now, if you also look at different objects, right? So we talked about graphs, right? But you also have grids, which are special cases of graphs, and you also have meshes, which are higher dimensional topological spaces, what is called simplicial complexes. So these are graphs with some extra structure. If you look at how a message passing or neighbor aggregation looks in these on these objects, so on a grid, we don't have any ambiguity, right? Because we have canonical ordering of the neighbors. I can designate, for example, my top neighbor, my bottom neighbor, and so on. On a mesh, I have slightly different situation. So I can designate my first neighbor, but then all the rest of the neighbors can be ordered, for example, in clockwise orientation, because meshes are locally Euclidean, right? So these are discrete manifolds. So the ambiguity is up to rotation. And graphs, as we've seen, any permutation would do, right? So in a sense, graphs have the least structure. Now, another thing that you notice when you look at these objects is that in the first two cases, I can easily imagine a grid as a discretization of the plane, for example, or a mesh as a discretization of a two-dimensional surface or a manifold. We don't have this analogy for graphs. So a graph already comes in the discrete form, right? So, and it's an interesting question. Can we actually come up with continuous models that, when discretized, give us graph neural networks, right? So what would be the kind of underlying physical system that we can derive graph neural networks from? And I will try to motivate you actually why you would like to do it, right? So that's what we call physics-inspired graph neural networks. And the metaphor for this is the following. So imagine that you have a collection of particles living in your high-dimensional feature space, right? And particles move along some trajectories, shown here by these red curves. And basically, it's a dynamic system, right? So particles can interact with each other. They have some rules that describe their evolution, and these rules are given in the form of differential equations, right? That are shown here. And the differential equations are coupled, right? So some particles interact. So if you discretize this system of equations, you get layers, right? Or steps of iterative solver that you would typically apply in physics to simulate it. And the graph is just a coupling function, right? So it tells you which particles interact with each other, right? So it defines the rules of interaction. Or, as we'll see, it can also be considered as a discretization of some continuous space, right? So space where these particles live. Same way as you discretize PDEs, right? And you have some local rules, basically numerical spatial derivatives. Now, you can come up with a lot of different evolution equations that appear here, different types of physical systems where these particles interact. Probably the first obvious thing to do is to consider diffusion equations, right? Or heat equations, as they are sometimes called. And this is probably one of the very old physical processes that have been analyzed rigorously by none less than Sir Isaac Newton himself about 300 years ago. And he experimented with how how hot objects lose their heat, right? And he measured their temperature and came up with a law that was given nowadays the name of Newton's law of cooling. And it tells us that the temperature that a hot body loses in a given time would be proportional to the difference between the temperature of the object itself and its environment, right? So this is a kind of global rule if we apply it locally on a graph, right? So you can apply it to any stuff, and you can apply it also not necessarily to heat, to diffusion of anything. It can be from, for example, from diffusion of a chemical substance to the diffusion of wealth in a social network, right? So it can be very abstract notions. So this is how it looks like. So we have some property that we are diffusing on the graph. And then we have the temperature of, right, or property of the node itself, right? So that's xi here. Then the rate of temperature change instantaneously, it's the temporal derivative. And then the temperature of the environment is the average or weighted average of the neighbors around this node, right? So if I slightly massage this formula, I can write it like this. And I can write it in abstract form in the following way. So what we have here is what is called the gradient. So that's the graph analogy of the classical gradient operator from classical calculus, right? So it's the difference between the endpoints of an edge, right? And what is written here is the divergence. So it's the joint of the gradient. It's also a classical differential operator that takes all the features on the edges of the graph and then sums them together, right? Over all the edges that emanate from a node. So the gradient takes you from nodes to edges, and the divergence takes you from edges to nodes, right? Bottom line, when we combine these two operators, the divergence of the gradient with plus or minus notation, depending on different references, is called the Laplacian operator. So the Laplacian tells you locally how different you are from your neighbors, right? And this is a very important operator that appears more or less in every equation of mathematical physics, from quantum mechanics to wave equations to classical heat equations, optics, wherever, whatever you want. And this is the simplest example of heat equation or heat diffusion equation, right? What is called the isotropic homogeneous heat equation. Now, heat equation is also a prototypical example of a gradient flow. So if you don't know what a gradient flow is, you probably know what is steepest descent, right? So that's how we train our neural networks. So it's a kind of evolution equation, differential equation that goes in the negative direction of the gradient of some energy that I denote here by E, right? So we have some energy that you minimize by this evolution. And the special type of energy that is associated with the heat equation is what is called the Dirichlet energy. So it measures how smooth your node features are, right? So how different you are from your neighbors. And it decreases along this gradient flow. And in the limit, if I run the diffusion for infinity, everything will be the same, right? So my neighbors will be equal to me, so the Dirichlet energy will be 0. So my neighbors, there is communism on the graph, right? So everything is the same. And it's not necessarily a bad thing, right? So it is typically associated with what is called over-smoothing, but you can think of a diffusion equation as a way of propagating labels of some known nodes. And if you assume that the graph is homophilic, or the data that lives on the graph is homophilic, meaning that my neighbors are similar to me, then this could be a very powerful solution, right? So it's diffusion equation with boundary conditions. So I know how information looks at some nodes, and I try to interpolate the missing nodes by propagating this information. So, of course, when the homophily assumption is broken, and that's what typically happens in real-world applications, then we need to do something more interesting, right? And that's where we need machine learning. And this gradient flow framework actually allows you to derive graph neural networks, or maybe more generally, deep learning architectures with some theoretical guarantees, so that we can call maybe very broadly some form of interpretability, right? So again, if you look at this physical metaphor, the dynamic system, so typically how you would design a traditional graph neural network, you will start with a set of differential equations like the diffusion equation. You will discretize it, and you will parameterize every layer of this equation, right? So you parameterize the evolution equations. With the gradient flow framework, you start with an energy, and you parameterize the energy, and then you derive the evolution equation as a gradient flow. And by doing this, you automatically restrict yourself to some subset of possible evolution equations that are not as general. So it allows you to make some architectural choices, or forces you to make architectural choices in order for this evolution equation to be a gradient flow. But what you gain is better interpretability, in the sense that you would be able to guarantee that certain phenomena happen or do not happen, right? And to give you a concrete example, so here's a example of a graph. So here, every circle represents a node. The colors represent labels that are unknown, right? Or in this example, you might know some of them. And the positions represent feature coordinates, right? So this is a dynamic system. So these nodes live in two-dimensional space and evolve in time, right? And the task here is node classification. So you notice that this graph is perfectly heterophilic. So the blue nodes have red neighbors, and vice versa. And yet we can find basically the energy that we consider here is a kind of pairwise interactions that are guided by this matrix W, that is the set of parameters, and it determines which directions in this space correspond to different interactions. When we have two types of interactions, we have attraction and repulsion, that correspond to the directions of positive and negative eigenvectors of this matrix W. And you see we can find two directions that are shown here, that the horizontal direction corresponds to repulsive forces, and the vertical direction corresponds to attractive forces, that completely separate perfectly these two clusters of blue and red nodes, right? And if you write the gradient flow of this energy, it looks like this diffusion equation with channel mixing. So we have, on the left-hand side, we have the diffusion operator that averages information in the neighbors. And on the right-hand side, we have some linear transformation of the node features. So basically, these are the direction in the feature space where the particles move. And we can guarantee in the form of this theorem that informally says that if I run a linear graph diffusion, right, so that's what we call convolutional GNN, where the aggregation depends only on the structure of the graph, but not on the features themselves. And we make some educated choices about how this matrix W is structured. So in particular, it must be symmetric and have sufficiently large negative eigenvalues. Then we, for example, can guarantee that oversmoothing will not happen. So will not converge to the situation when all the features are the same. So in this diagram, they will all collapse into a single point. So we can guarantee that this doesn't happen. So more technically, what happens here is high frequency dominated dynamics. So we have some kind of sharpening, not only blurring effect. And it allows us to work both in homophilic and heterophilic settings without losing the advantages of the graph neural network architecture. Now, of course, this is just the simplest example of an homogeneous diffusion, and actually these ideas of applying a PDE to your data that lives on some geometric domain have been very powerful in image processing about 30 years ago. And you can see that on a grid, this diffusion equation can be represented by convolution. So if I run the diffusion equation on this face of Isaac Newton, what happens is that basically the solution is given by convolution with the Gaussian, whose standard variation increases with time, right? So it's a low pass filter. So if I run it for a longer time, it becomes blurrier and blurrier, right? And this is how the kernel of this local operation looks like, right? So it's Gaussian. Now, this is obviously not nice because I can, if the task is denoising or some image enhancement, I average out the noise, but at the same time, I also kill all the nice visual features, these continuities in this image. So what was derived in the seminal paper of Perron and Malik in the 90s was to consider a nonlinear diffusion that is adaptive. So the adaptivity here comes in the form of a different diffusivity constant that is not the same at every point in the image. It is proportional to the discontinuity in the image, right? So the idea is that you don't diffuse across edges. So I don't mix pixels of different color. And the kernel will look like this. So it will have this kind of bilateral structure. So it will average only on the dark side, right? But not on the bright side and vice versa. And this is what is called a non-homogeneous diffusion. They erroneously call it anisotropic. It's actually isotropic, but non-homogeneous. And you can derive the same thing on a graph. So on a graph, you will have a learnable diffusivity function. And you can actually see that if you discretize in a certain way this equation with forward derivative with what is called the forward Euler discretization, and you normalize the diffusivity and choose unit step size, then you get the classical graph attention networks. So you can show that many existing architectures can be obtained as a particular discretization of this kind of nonlinear diffusion equations. So it's very interesting, very broad framework that allows you to basically to derive from discretizing a well understood physical system. It allows you to derive existing architectures, and then of course you can apply a lot of knowledge that we have in numerical analysis and the theory of differential equations to guarantee or to analyze the behavior of these systems. Now, I promised you that we will also have some continuous representation of the spatial part, right? And so far we discretize only the time, right? But it's interesting, actually, how can we think of a graph as a discretization of some continuous objects, right? And again, if you look at how diffusion looks in images, so you can think of an image as a function that lives in a plane and then it's discretized on a grid. And for example, if you take the Laplacian, these are different ways of discretizing the Laplacian on a grid, right? And any convex combination is also a valid discretization of the Laplacian because it's a linear operator. So my main message here is that we don't really have a canonical graph when we solve the equation, differential equations on the plane. And we would like to adopt the same mindset for graph neural networks. So that's our version of graph rewiring, right? So that the graph is kind of convenient discretization of some continuous thing. And in order to do it on graphs, again, let's look at images. And instead of considering this nonlinear diffusion, let's consider a non-Euclidean diffusion. And you can think of an image as a surface or a two-dimensional manifold that lives in a joint space of positional coordinates and feature coordinates, right? So an RGB image will be a two-dimensional surface in five-dimensional space that every pixel has X, Y coordinates and also R, G, and B feature coordinates, right? So if it's a manifold, by virtue of this embedding, we can pull back a metric, right? So a 2x2 matrix that defines locally the structure of this manifold. And we can derive a diffusion equation that instead of the classical Laplacian uses what is called the Laplace-Beltrami operator, the non-Euclidean version that is used in differential geometry. And then we can derive it also as a gradient flow of what is called the Polakov functional. So it is used in high energy physics, in particular in string theory. So the same thing can be applied to graphs. And now every node is equipped not only with feature coordinates, but also positional coordinates. And it can be also positional coordinates in some other space, not necessarily Euclidean, like hyperbolic space. And then we diffuse again with learnable diffusivity, both pairs of coordinates, and the evolution of the X dimension of the features results in the usual feature diffusion, and the evolution of the positional component can be considered as some soft version of graph rewiring. So if nodes come close together, we can connect them by an edge, and if they drift apart, we can cut the edge, in order to facilitate the flow of information for the downstream task. And you can see an example of node clustering. This is what happens in this example. So three things are happening. So the feature diffusion, right, that is represented by car. Positional encoding also changes. So that's how the circles move around, and also the graph is rewired on the slide. And this is a kind of disturbing picture if you come from signal processing perspective. So we have a domain that is changing while we are filtering the signal that lives on this domain. But actually in differential geometry, this is a very common picture, and it's common to take a domain, a manifold, and evolve it by some evolution equation. One classical example are Ricci flows that actually structurally look very much like diffusion equations. So you can think of it as a kind of diffusion of the metric tensor, right? So we have the Riemannian metric on the left-hand side, right, in simple derivative, and the right-hand side is also a second-order quantity that is called the Ricci curvature tensor. And basically what it does to a manifold, here it is colored by its curvature. So it becomes more like an ellipsoid, and then becomes more like a sphere, and then collapses into a point. And famously, these Ricci flows were introduced by Richard Hamilton with the goal of proving the Poincare conjecture. That was indeed the tool that was used by Perelman famously about 15 years ago to prove the Poincare conjecture. And it was a big insult to topologists that here comes the differential geometry and proves our Holy Grail problem. The way it works, basically, what Poincare conjecture, that in 2 dimensions you can characterize a sphere by the ability of collapsing a closed curve into a point. You can do it on a sphere, you cannot do it on a torus always, right? So, and the conjecture was that it works in high dimensions as well. Now, what does it have to do with graphs and graph neural networks? So in graph neural networks, we have the phenomenon that I mentioned, oversquashing, when the graph has its property that the volume grows very fast, right? When we have a lot of neighbors of the neighbors of the neighbors, right? And we also, the function that we need to compute on the graph requires long-range interactions, right? So these 2 different things. So the volume growth is related to the structure of the graph, to the graph topology, and the long-range interactions relate to the task that we want to solve. So the way that we can describe oversquashing mathematically is that if I give you a multi-layer message passing neural network with some properties like number of layers, certain internal dimension, and so on, I can ask, if I change the input at some node and I look at the output at some distant node, how it will be affected by this perturbation, right? And I can measure it, I can capture it by a partial derivative that is called the Jacobian. And basically, if this derivative is small, it means that information is somehow lost, right? So this perturbation in the input doesn't propagate well to the output. And what we show in our paper is that we can bound this perturbation, this Jacobian of the neural network, by some constants that depend both on the model, right, on the architecture of the GNN, the number of layers, and so on, and also by the graph topology. And intuitively, we expect that topology plays a crucial role, because something like a grid probably will not have this phenomenon of oversquashing. On the other hand, something that looks like a tree probably will, right? And we need something more nuanced that would allow us to distinguish between these 2 structures. And that's exactly what curvature was designed for. So in differential geometry, curvature, you can think of it as what is called geodesic dispersion. So if I have nearby points and I shoot geodesics from them in parallel, I can trace them and see if they converge, diverge, or remain parallel, right? And this can be quantified by a single number that is called curvature. And it allows us locally to tell apart between spheres and hyperboloids, right? Or planes. So the same thing can be generalized to a graph, right? So you look at certain number of structures like triangles and rectangles. So it's an age-wise quantity. We call it discrete Ricci curvature. And we show that these bottlenecks, the oversquashing phenomenon, can be attributed to strong negatively curved edges in the graph. And once we know it, we can design some discrete process a little bit analogous to the Ricci flows that cuts out edges with negative curvature and replaces them with edges with bigger curvature, and makes graph neural networks work better. So the graph becomes friendlier for message passing. Now, what is the problem with this approach and other approaches for graph rewiring? So we understand how to make a graph better for the flow of information, but there is no relation to the task whatsoever. And I argue that the task is extremely important, because I can give you a graph with exactly the same structure, with exactly the same features, but the task that I want to compute on this graph might be different. And in one case, using the graph for propagating information to compute the task might run into problems, and in others won't, right? And the good example, again, comes from the world of physics. So if I give you a molecule, I can have different types of interactions in a molecular system. So what is called van der Waals interactions that decay very fast with space, I think 1/r to the power of 12. And electrostatic interactions, Coulomb forces that decay as 1/r. So this is how this interaction looks like, right? Visualized. So in the first case, I only need my local neighbors. I don't care about these neighbors because these forces are completely imperceivable far from an atom. In the second case, probably the interactions of all the nodes matter, right? And again, this is same graph, same features, different task. And whether the graph is good depends on the task, right? So I cannot a priori say that this graph is good, this graph is bad, right? So it really depends on the task. And this is what we call long-range interactions. And by task, I mean a function that is defined on the nodes of the graph and depends on the structure of the graph and its features. And the interaction between different features, again, can be quantified using this now second-order partial derivative, what is called the Hessian. So we call this mixing, basically how strongly two distant nodes in the graph interact. And we can again describe the capacity of message passing graph neural network with certain number of layers and Lipschitz constants and so on. And we can ask what is the capacity that is required for a given task. So in other words, if I give you a task that requires certain mixing, can a message passing neural network of certain architecture induce this mixing, right? And we can bound the mixing, right, that is related to the task by some constants that relate to the model and the topology of the graph. So the capacity depends on the model and the topology, and the task is quantified through the mixing. And we can, for example, show bounds on the weights in the graph neural network and the depth of the graph neural network, and for example, come up with impossibility statements. So we can show that for some tasks, the graph neural network must be of certain depth that sometimes can be intractable, right? So it can be of order of the number of nodes, which is of course not something that we can practically implement because graphs can be with millions of nodes. So it gives an alternative way to the Weisfeiler-Lehman formalism to describe the expressive power. So we can say that with less than certain number of layers, you cannot mix, you cannot learn a certain task. Now, I think I have probably a few minutes left, so I wanted to talk about manifolds in geometric graphs. And this is another incarnation of the geometric deep learning blueprint. And you may think that manifolds are quite exotic objects that are studied in pure mathematics, right, in differential geometry, but actually they are very practical when it comes to describing three-dimensional objects. So if I look, for example, at my own body, right, so if I don't care about what happens inside, only the outside surface that basically you see, right, it is much more compact representation to describe it as a two-dimensional surface rather than three-dimensional volume, right? And then we can use constructions from differential geometry also to account in a convenient way for the deformations that these objects can undergo. Now, why this is important, for example, in problems of drug design, when we model how proteins interact, right, or molecules interact. So here's an example, a plastic model of a protein. So it has this very complicated, intricate folding. And you know that predicting the folding of a protein is a very hard problem. So they took 50 years finally get to the level where you can do it, famously with AlphaFold of DeepMind. But when two proteins interact, actually what matters is only somehow the outside molecular surface. It doesn't matter what happens inside the protein, right? So basically by thinking using the right representation, you can abstract out the relevant information and make a very difficult problem into a much easier problem. Now, when it comes to the manifolds, and allow me to skip the details, roughly we have two types of symmetry or two types of invariance. So we can have invariance to some kind of global deformations. So if I stretch and deform this manifold, I want to say that nothing happens, right, in some sense, right? Or there will be also some kind of ambiguity related to the local choice of coordinates, right? So what are manifolds? Manifolds are local Euclidean spaces, right? So formally, these are topological spaces where you can associate with every point a Euclidean space, in this case of 2 dimensions. This is a 2-dimensional manifold surface. And on this space, we can define what is called the Riemannian metric. So it's a local way of measuring distances and angles. And anything that is described in terms of this metric is called intrinsic, and isometries are metric preserving deformations, right? So that's what you need to know about differential geometry. Now, I can also define a mechanism that is called exponential map. And it's also an intrinsic quantity that allows me to fetch information from the manifold, right? If I have some property, some function that lives on the manifold, and bring it to this local Euclidean tangent space. And now I can work in the tangent space, so I can define analogies of this kind of local neighborhood aggregation or convolution on the manifold, right? Now, because everything here is defined intrinsically, so this construction is automatically invariant to isometries. And this is how these filters might look like. So these are example of these local kernels that they can define. So it looks like, well, we solved the problem, right? So we have a definition of the convolution, but what is written here is actually cheating, because when you are explained what vectors are at school, at least this is what I was taught. So usually it's told that vectors are, you can think of them as a kind of arrows pointing in different directions, or you can think of them as coordinates, right? Actually, none of this is true. So this is crime against humanity to teach that vectors are arrows or coordinates. Vectors are abstract objects that you can add and scale, right? That's it. So, or you can, as mathematicians like to define things in a bit paradoxical way. So vectors are elements of a vector space, and vector space is something that has these rules of scaling and addition. So these are not, basically these are vectors, right? But we don't have a way of manipulating them. When we want to represent them on the computer, we must represent them as arrays of coordinates, as matrices. So we must assign some local frame, some local system of coordinates in order to do it, right? So in order to think of vectors as arrows, you need an inner product, you need a notion of direction, so it must be Hilbert space. And in order to think of them as coordinates, you must have some reference frame, some system of coordinates. And the problem is that the system of coordinates is ambiguous. It's defined up to what is called the structure group of the manifold, which in case of Riemannian manifolds is the special orthogonal group, or this orientation preserving rotation. And you can define filters in a way that will be equivariant with respect to the choice of the system of coordinates. So again, this will be this kind of local symmetry respecting way of aggregating information. And bottom line, what you get out of this complicated way of dealing with manifolds is that you have filters defined on the manifold itself, and you basically by smart architectural design, you make filters that deform together with the manifold, and basically the network comes equipped with a lot of invariance. Might be important in problems where your three-dimensional objects are deforming, and one of them is, for example, motion capture in computer graphics, where you want to transfer information from a captured face in real time of an actor to this synthetic creature that you want to put, for example, as an avatar in your interactive game. And you can do it also from two-dimensional inputs. So you might have, for example, a standard two-dimensional convolutional neural network, and then the synthesis is done by a geometric deep learning architecture. So that was work of my PhD student, Dominic Coulon, collaboration with a British startup, Real AI, by my colleague and friend, Jasnas Kokinos, and they were acquired a couple of years ago by Snap. So you can probably now find this technology powering some of their features. Let me just finish with a few minutes with examples of applications in molecular design. So this is probably one of the most promising examples of where geometric deep learning will make an impact, in my opinion, in the next 5 to 10 years. And as you probably know, basically we all are proteins. So this is what is encoded in our DNA. So a sequence of 4 letters organized into triplets, what is called codons, encode amino acids that in the cell produce this sequence of amino acids, or basically biological molecule, a biological polymer that under the electrostatic forces folds into this complicated 3-dimensional structure, right? And it was predicted by Anfins and Nobel laureate in chemistry 50 years ago that the sequence determines the structure. And indeed, a few years ago, DeepMind was able to show that they can actually compute it. When you design drugs, you're actually interested in the converse process. So you know how your structure should look like, but you try to design a sequence that would fold in this structure. And it's compelling to think of proteins as basically these levels of abstraction of sequences that are one-dimensional strings. And actually first methods in bioinformatics looked at strings because it's very easy to deal with them. Then from sequences, you go to structures, and that was a big problem in structural biology. And then structure somehow endows the protein with its function. For example, what kind of molecules it binds or interacts with. And the metaphor here is the lock and key metaphor. Same way as you have a unique key that enters and fits into a lock. Basically, that is complementary to the configuration of these little knobs inside the lock. Same way, there will be just a single molecule that binds your protein, some kind of pocket that exists on its surface. And this is how most drugs are designed. So you try to fit a small molecule into a pocket on the protein surface that you identify as important target in your disease. So this is how, for example, when we drink coffee, this is what happens. This is how caffeine or similar chemical compounds bind the adenosine receptor in the brain. And graph neural networks have been used to predict very fast molecular properties that would be important for certain class of drugs like toxicity, solubility. Also, they are function against, for example, pathogen. And probably the biggest success was a paper from MIT where they used graph neural networks in a screening pipeline to discover new antibiotics. And they discovered, for example, that an anti-diabetic candidate drug, halicin, had important properties against antibiotic-resistant bacteria. Now, many drugs or many interesting targets do not have these pocket-like structures. So you cannot typically find a small molecule that will bind this. And this typically happens when two proteins come together and interact. So these protein-to-protein interaction targets are important for the pharmaceutical industry. They happen, for example, in oncological therapies, what is called immunotherapies for cancer. So the two proteins that are shown here, they're called what is called program death complex. So it's two proteins that show the immune system that this is a healthy cell. And as a result, it is not destroyed by the normal functioning of the immune system. And some cancers produce these proteins, so they become untouchable by the immune system. So immune therapy, in very simplistic terms, blocks one of these proteins by when you introduce another protein. So it's difficult to drug by a small molecule, but you can drug it by a biological molecule, by a peptide or a protein or an antibody. And there are already some successful drugs on the market that target either PD-1 or PD-L1 proteins. And something that might have been a death sentence a decade ago now is perfectly curable. And these are called biological drugs or biologics. So the big question is how to design them. So typically they're designed by evolution. So you just throw your targets, right? And you, for example, you inject them into a mouse and you try to get antibodies that respond to this target protein. It doesn't happen all the time because, well, it's a natural process. When you're isolated from a biological system that, for example, maybe some parts of this protein are intracellular and not exposed. So it's much better to try to design this protein computationally. And this is what I did with my collaborators from here, from Lausanne, the group of Bruno Correa. So this is a geometric architecture that we call massive. And it allows us to rationally design proteins that with certain properties like binding to a desired target. And here are examples of binders that we designed for PD-L1 oncological target. And here you can see it's X-ray crystal structure, so it's actually very accurate. And here's another example. So this is probably one of the most studied proteins in the recent years. So the spike protein of the SARS-CoV-2 coronavirus, the one that was responsible for the COVID-19 disease. So here we also see, for example, neutralization of pseudoviruses and also efficiency against different variants. That is, if you remember a couple of times, probably everybody was looking in newspapers. Is there a new Omega or Omicron that is emerging and might get us sick? So just to conclude, this is how this field might evolve. So we are interested in these generative AI models where you can design a molecule same way as you design an image in response to a prompt by DALL-E or Midjourney model for images. You may imagine maybe a few years from now, you will have a similar system that generates a molecule with some conditions, for example, on how the geometry of the target looks like, or maybe some additional constraints. You can do it in many different ways. In some recent works where we show that, for example, you can assemble little fragments, what is called pharmacophores, into a bigger structure by a diffusion model that connects them together. So I would like to finish with a quote. I started with one. I would like to finish with another by actually a local guy, Helvetius, famously said that knowledge of principles compensates for the lack of knowledge of facts. And I think this is the guiding principle of geometric deep learning, or I think how machine learning should look like. So it's a deep mathematical discipline rather than collection of hacks. So thank you very much.
Thank you so much. Thank you so much. Thank you so much for a fantastic talk. I love your slides. Slides are awesome. Are there questions in the room? Maybe on, then we can go online. So there is somebody is raising his hand. Is there a mic?
The permutations that were taking place toward sort of the middle of your presentation, they remind me a lot of Steiner sets. Have you been, I don't know, working with Steiner sets and maybe Lyapunov?
So, short answer, no. There might have been some papers, yeah, but I'm not aware of that.
Okay.
So we have a question online. So you point toward transformers that may help to correct the graph structure. And somebody asks if there is an equivalent to learning the correct manifold.
To learning a manifold, that is when discretized becomes a certain graph. It's a good question. So, so first of all, we have, well, there are some maybe exotic papers. So one of the things that when you, for example, in problems like link prediction that I didn't talk about, so you try to embed the graph in space where the proximity between the nodes corresponds to the probability of having an edge, right? So you try to create an embedding that preserves the local structure of the graph. And usually there are no isometric embeddings, so there are some mistakes in doing it. Now, this doesn't account for the higher order like triangles. So you can try to do an embedding into an exotic manifold that has controllable curvature. And the curvature can be controlled in a way that matches the curvature of the graph. So in this sense, you can try basically to fit the manifold, some manifolds. So the manifold will typically look like a product with some base manifold and local spherically symmetric component that you can basically control the radius, and by doing this you control the curvature without affecting the distances. So this is what we've done. Yeah, probably there are many other ways of doing it.
More questions? More questions in the room? So maybe I have one question, which is, so often in deep learning, being nice GPUs, being following their structure is very important, because it's really, I mean, computation is key. And so what price do you pay when you do GNNs in general? So yeah, what is the overhead in terms of compute?
Yeah, it's a very good question. So if you look at the, so first of all, maybe more on a philosophical level. So there is this, what is called the hardware lottery phenomenon, that it is the right match of an algorithm and a hardware architecture that is winning, not necessarily the best algorithm, not necessarily the best architecture. This is what happened with convolutional neural networks, right? So GPUs are what is single instruction, multiple data architectures, allow you to apply the same operation very efficiently many times, right? So roughly. And you can argue that, well, in images, you also have rotation. So why not to use, for example, some bigger groups rather than translation? It's the fact that it is very easy to implement convolutions on the GPU, or previously on a DSP. This was really the big thing about the paper of Lecan in the 80s, that he implemented it in real time on the first digital signal processors. Now, to graph neural networks, you can think of them as sparse matrix multiplications. Now, it depends on the hardware when this is efficient. I heard people from NVIDIA say between 5% and 10%. Sparsity beyond this, it's already worthless. So you can already use dense matrix multiplication operations. So you don't gain much from the sparsity. But if the graph is sparse, you can benefit from sparse matrix multiplication. So this is with GPU architectures. Now, there might be other architectures that are not GPU that are different, and well, NVIDIA and other semiconductor companies are looking into designing future generations of architectures that might be more favorable or maybe more tailored to graphs. You can argue that maybe in the future everything will look like a transformer, which of course is the most friendly for GPU. Of course, it has very high computational complexity, so I think it's fair to say what will be the right successor for transformers when it comes to very large graphs or to very large sequences. And it's probably some kind of combination, so some sparse version of transformers that maybe also incorporate some geometric ideas.
Okay, thank you. More questions? Okay, or maybe we take one last, then we have to make the coffee break, but we can talk during the break.
Yes, since no one else wants to volunteer for questions, it's not a question, it's a reaction. I understood nothing except that it was fascinating. And why? Even an illiterate like me, that is a journalist, often thinks about chemistry and what the difference between mere cooking recipes, chemistry, then come back to my mind some memories of covalent, electrovalence, and I realized how ill it was explained and how open this field still is. And I think that what I heard today will help me in writing articles about that, to keep these questions open and not give to, let's say, academic and traditional description of thinking about molecular relation and things like that. So maybe I'm totally beside the point, but I was very much inspired, and we'll talk at the coffee break if you are available.
Thank you very much.
Okay, so let's maybe move to a coffee break, and thanks, Michael, again.